So in today's video, we're going to be talking about the derivative and what it is, the formal definition of it, and some common questions that get asked in the AP Calculus test about the derivative. So when we're talking about a derivative, it's really a concept that you're already familiar with. We're just putting it in more formal terms. So what a derivative is it represents a rate of change. That's really what a derivative means. So if I have like a deer population that is growing as time goes on, I could ask, well, how many deer are there every month? How many new deer are added to this population every month? And what that is that's a rate of change. Because I'm asking, as time goes by, how does my overall deer population change? How does it grow or decrease? So that's really what a derivative is asking. It's just how fast is something changing? How is it becoming different? Another way that we can talk about derivatives that you've already seen in math at this point is slope. So a derivative really means what is the slope if we're talking about some function. So we've seen with lines, with the y equals mx plus b that you've done a million times, the m represents slope, right? So if I had a line that would say y equals 3x plus 2, 2 is my y-intercept, and this line right here has a slope of 3. So that means I go over 1 up 3, over 1 up 3, over 1 up 3, and that is how I create my line. So you've already dealt with slopes with lines up to this point. So the derivative really is a somewhat familiar concept. We're talking about what is the slope of this line. So if we wanted to know what the derivative of this line was, that I've written here, this y equals 3x plus 2, we would say that the derivative of it is 3. And the notation that we use is this little tick mark right here, this apostrophe mark. This is read y prime. So that little tick mark means prime, and it means the derivative. So if I had this function y equals 3x plus 2, then y prime, or the derivative, is 3. So we're saying that the slope of this function is 3. So that's a somewhat familiar concept for you already when we're talking about lines. So where it gets a little bit trickier is if we're not dealing with these nice linear functions anymore. So let's say we had something like a parabola. We had the parabola y equals x squared. And we want to talk about the slope of this. Well, we know that if we're talking about a line, we just would do rise over run. So whatever the rise over run was, that's our slope. But what about if we're dealing with a parabola? It's a little bit different. A parabola doesn't have a constant slope like this line did, because this line we could just go over 1 up 3, over 1 up 3 and keep doing that forever, and that was always the slope of this line. But that's not true with the parabola, right? Because this parabola has a curve to it. It's not just over some number, up some number every time. Because a parabola does not have the same slope everywhere, right? Because right here it looks a little bit steeper than right here. That looks pretty flat. So that's why we need to, or it's useful to use the derivative, is that not all situations are nice linear functions like this. So this expression that I put up on the screen is called the formal definition of the derivative. So this expression formally and precisely defines the derivative. And we talked about the derivative being a rate of change or a slope. And hopefully by the end of the video, what you'll realize is that this expression actually represents a slope. So what I have drawn here are my x and y axes, and right here I've drawn for you some function. So I'm going to call this function f of x. It is some function. And then what I'm going to do is I'm going to label this spot on the x-axis x. I don't know what number value that is, but for the purposes of this, I'm going to just call that some x value. And then I'm going to call this horizontal distance right here h. So I'm starting at some x value, and then I'm going a horizontal distance of length h. So if I start at x, and then I go some length h, then I should end up at x plus h. Right? So I started here at x, I increased by some horizontal distance that has length h, so then I should end up at x plus h. That should be my ending point. And so now we're going to think about this spot on our function f of x. So if I plug in x into my function f of x, what y value should I get out at that spot? And well, if I plug x into my function, the y value I should get out should just be f of x, right? So f of x represents what the y value is at this point. And then if I go to the point that corresponds with x plus h, if I now plug in x plus h into my function, what y value should I get out? And well, if I plug in the value x plus h, my y value should be whatever f of x plus h evaluates to. So my y value at this point is going to be f of x plus h. So I've just decided to arbitrarily label this spot x plus h, and then these should be my corresponding y values at those spots. So now what I've done is I've drawn a straight line connecting these 2 points. And what I want to do now is I want to figure out what the slope of this straight line should be. So again, we talked about slope with linear functions. The slope of linear functions is just rise over run, because lines have the same slope everywhere. So the slope of this thing should just be rise over run. So let's think about what the rise of this should be. Well, the rise should just be this vertical distance right here. And the run should just be this horizontal distance right here. So what I've done is I've drawn a slope triangle for this blue line. So the rise is going to be that vertical distance, and the run is going to be that horizontal distance. So to find this vertical distance, if we want to figure out the rise, to find this vertical distance, well, what we're going to need is we're going to need the y values, right? So whatever the y value at this spot right here is, and whatever the y value at the spot right here is, if we subtract those 2 y values, we should get that horizontal distance right there. So what's the y value at this spot up here? Well, that y value is f of x plus 8. So the y value at the point right here is f of x plus h. And what's the y value at the spot down here? Well, the y value there should be f of x. So f of x plus h minus f of x is going to be the rise, that vertical distance of this blue line. So now what's the run? Well, the run should be this horizontal distance, so this side of our slope triangle. And we decided that that horizontal distance right there is just h. We decided to label that distance as just h. So our run is going to be h. So hopefully now you're seeing that this expression looks a lot like what we have up here. So without the limit part, if we're just looking at the f of x plus h minus f of x over h, that represents the slope of this blue line, right? It's a rise over run. And now what this blue line is called is this is a secant line. And a secant line is any line that intersects a function twice. So we can see that this blue line intersects my f of x twice. It intersects it down here and right there. So that is called a secant line. So now let's look at the last part of this formula, this limit as h approaches 0. So what does that mean? Well, we know that h is this horizontal distance down here, and approaches 0, that means that h is going to get really, really small. And so if h is this horizontal distance down here, by making it approach 0, we are shrinking this horizontal distance. We're going to make this horizontal distance smaller and smaller and smaller. So let's say we make this horizontal distance half of what it was. So what I've done here is I've made our h smaller. I've cut it in half. So if we were to do that, cut that horizontal distance h in half, then my new line, if I were to draw the new version of this blue line on here, its endpoint would be right there. And so that line is going to look something like that. So right here I've drawn a green line that connects this point and this point. So this green line is the new secant line that we get from splitting this horizontal distance h in half. So what we've done is we've made that horizontal distance h smaller. And you can see what happens to the line that we've created if we do that. The endpoint ends up right here of this line. So if we're going to take h, we're going to take the limit as h approaches 0, we're going to make h smaller and smaller. That means that what we're going to do is we're going to make the endpoint of this secant line get closer and closer to this starting point, right? Because for our blue line, the endpoint was all the way up here. But when we cut h in half, the endpoint ended up being right there. And then if we keep shrinking h, we keep making that horizontal distance smaller, our endpoint will end up there, and then there, and then there, and there. And so I think you get the idea. The endpoint, if we were to draw a new line each time, would end up getting closer and closer and closer to where we started. So what's happening here is we started with this blue line, we started with a secant line, and by making that horizontal distance h smaller, we are shrinking this line and turning it into a tangent line. And what a tangent line is a line that intersects a function only once. So what I've done here is I've put this yellow line in here, and this yellow line represents a line that is tangent to my function f of x right at that point. So you can see that this yellow line only touches my black function once. It only touches at this point. So that's what makes it a tangent line, is that it only touches my function once, whereas this blue line that we drew touches my function twice. And so the reason why that's so important is because if a line is tangent to a function, that line will have the exact same slope as that function at the point they touch. So meaning if I were to find the slope of this yellow line here, let's say the slope of this yellow line was 3, then my black function f of x would have a slope of 3 right at this point. So that's really significant because it allows us to find an exact slope of a function that's curvy, right? Before this video, we only knew how to find the slope of a line if it was straight. But now what we can do is even if we have a curvy function, we can still figure out the slope by finding the tangent line. So that's what this expression right here says. So let me put that limit part out front. So this fraction part, the f of x plus h minus f of x over h, that represents the slope of our secant line, the blue line. And then when we add on that limit piece, the limit as h approaches 0, that takes our secant line and turns it into a tangent line by making that horizontal distance h smaller and smaller. So without the limit there, without the limit part, this fraction is just an approximation. It's a guess at the slope. But the limit makes it exact, right? Because as soon as we have a tangent line, we know that it has the exact same slope as the function it's tangent to at that point. Now, this is a really common mistake, so I want to make this really clear. This yellow line, my tangent line, only has the same slope of my black function at the point they touch. As soon as they're not touching anymore, they do not necessarily have the same slope. So don't think that the tangent line slope is going to be the exact same as my black function slope everywhere. They're only the same at the point that my function and my tangent line touch. If you wanted to find the slope of my black function like up here, then you would have to find the tangent line at that new point. So make sure that that idea is really clear because a lot of people get tripped up on that. So the tangent line and your function only have the same slope when they touch. So now that you have a little bit of an idea of what this expression means and where it comes from, how it's really taking the slope of a secant line and turning it into a tangent line, I want to look at a kind of problem that is very commonly asked, not only on the AP test, but also in AP classes. And so it'll look something like this. The problem will give you the expression, the limit, as h approaches 0, of tan x plus h minus tangent x all over h. So this is what the problem will give you, and it'll say that this expression right here, the expression you're looking at, is the derivative of a function. What function is it the derivative of? And so maybe they have some options, say maybe it's the derivative of secant, maybe it's the derivative of 3x plus 2, I'm just making these up. Maybe it's the derivative of tan of x, and maybe it's the derivative of x squared. So you're looking at all these different functions and you're going, okay, which one has their derivative pictured here? And so this question is all about being able to look at this and recognize that it is this formula up here, just with a specific function plugged in. So up here in our formula that we started with, we were just using the notation f of x. F of x just means some arbitrary function. It just stands for like, hey, there is some function here, but we're just going to use a general name for it. But now you can see that instead of f, we have this function tangent in here. So what this is the formal definition of the derivative of the function tangent. And how you would know that is if we look at our original formula here, it's f of x plus h minus f of x. F of x is what we're looking for, right? F of x means this is the function that we're dealing with. And so if you just look for whatever comes after the minus in this formula, that should be the function you're taking the derivative of. So the answer to this would be C. And all we're doing is saying, hey, this is the formal definition of the derivative, and I know that that has all these component pieces. Can I pick out which piece tells me which function we're taking the derivative of? And so that is always going to be this piece over here, because in our original formula, we subtract f of x, our function. So that's a really common question that teachers love to ask, just because you don't have to do anything too tricky with the formal definition of the derivative, but you have to be able to look at it and go, boom, that's the formal definition of the derivative, and I know what each piece means. And I'm able to work backwards a little bit and pick out the function that we're taking the derivative of. So hopefully this video was helpful and a nice introduction into what a derivative is, just slope, and then how we formally define it. And again, we're really just dealing with slope triangles here. This fraction represents a secant line, and then we turn it into a tangent line by taking the limit as h approaches 0. So also make sure you're comfortable with the vocab secant line and tangent line. Most importantly, you will be using the word tangent line a million times in your calculus careers. So make sure you remember what that means, the significance of it, and how to draw one on a graph. As always, make sure to leave any comments, suggestions, improvements you have, any other topics you would like to see in the comments, and make sure to give it a subscribe.